Hello and welcome. In this video, we're going to learn how to integrate using U substitution. So let's jump right in. What I would like you to do first is actually find the derivative of each of these three functions up here, A, B, and C. So go ahead and pause the video and work through that. All right, hopefully you remembered your chain rule and you correctly found the derivative of each of those functions, and this is the simplified version here. Now, what I want you to notice is that on D, E, and F, I want you to think about what you just did in A and B and C, and think if we know that this is what is inside, what would that original function be? If this is what's inside, what would my original function be? So go ahead and pause the video and see if you can work backwards to find the antiderivative or to integrate what you see there based on your answers in A, B, and C. So hopefully you notice that what I see there on the inside is the derivative of, for part D, this is the derivative of part A, which means if I undo the derivative, what I have here is what I originally had in part A, but I'm not going to forget my plus C. Similarly, for E, what I have here is what this should say cosine, shame on me. What I have here is the derivative of what I found up here. So if I undo taking the derivative, if I integrate, I should move back to having sine of 1 plus 5x, and then I'm going to have plus c because I'm integrating. Similarly, f, the inside is the derivative of the function that we found in c, so the antiderivative would just put us back at the square root of 7x to the third plus some arbitrary c value. So in A, B, and C, when we were finding the derivative, we had to use the chain rule. So what we're going to start to think about is, how does the chain rule affect integration? How do we undo the chain rule when we're integrating? So that's where we're going in this lesson today. So to deal with the chain rule when we're integrating, or I guess more specifically to undo the chain rule, we have to think about what the chain rule does. When we perform the chain rule, we sort of hook on the derivative of the inside function. When we're taking that derivative, we take the derivative of the outside and keep the inside the same, and then we multiply that by the derivative of the inside. So when we're undoing that process, we need to unhook, we need to get rid of that inside derivative when we're integrating. The easiest way to be able to visualize what's going on here is to actually manipulate the integral using U substitution. So whether or not you recognize that what you see is the derivative of a chain rule situation, you should still be able to evaluate more complicated integrals than we have been doing using U substitution. So what you will do is you will define U to be equal to a particular part of your integrand. Then you will look at what happens when you take the derivative of that part, and then you will rewrite your expression as an integral with respect to U. So let's look at those steps in a more dynamic way and work through an example while we talk about each step. So the very first thing that we're going to do is we're going to determine what U is. Typically, the very first thing you want to check, or that you want to try, is to let U be equal to the inside function. So the insidemost function here is x squared plus 1. So I'm going to say let U equal x squared plus 1. Then you're going to take the derivative of both sides. So if I take the derivative of U, I get du. If I take the derivative of x squared plus 1, I get 2x dx, right, with respect to x. Now, I can replace this part of my integrand with U, but I need to also find a way to replace dx with U. If I'm going to rewrite this integral to be in terms of U, I need to rewrite dx to be in terms of du. So we're going to go ahead and solve for dx here. So I'm going to divide both sides by 2x so that I can say that dx is just equal to du divided by 2x. So now this is going to get substituted into my integral for 2x. This U is going to replace x squared plus 1. So let's rewrite that whole integral using all of our new information. So we have the integral of now that part became u, and what were we doing to x squared plus 1? We were squaring it. Times 2x, I haven't done anything with that 2x that was here yet. And then instead of dx, I'm going to put du divided by 2x. What you'll notice here is that I have 2x divided by 2x, so that's just going to divide away, and I'm going to be left with the integral of u squared du. Well, here's the nice thing. This integral we can evaluate pretty easily just using the power rule. So what we did in step 3, well, step 1 and 2, we defined our u and we determined du in terms of x and dx. Then we substituted back in, and now we have an integral that we can evaluate. So we're going to look at step 5. So if I evaluate this, I'm going to add 1 to the exponent, and I'm going to divide by 3. And since there are no bounds on this integral, it's an indefinite integral, I need my plus c. Now remember, this original problem was in terms of x, so my final answer also needs to be in terms of x. But that's not a big deal. All I need to do is take everything that's here, and then where there was a u, plug in what I defined u to be at the beginning, x squared plus 1. So you're going to start by defining your inside function to be u, taking the derivative of that, and solving for dx. Then you're going to rewrite your whole integral with u and du. Then, hopefully, at that point, you're going to be able to evaluate what's there, and then you're going to substitute x back into your original equation. So let's look through some examples that are really similar to the one that we just did. Okay, here we go. When I'm looking at number 1, secant squared x times tangent x to the power of 3. We don't know how to integrate this right now because I have the product of secant squared and tangent of x to the 3rd. That's not something that automatically looks like the derivative of something else. That's what's indicating to me here that I'm going to try to use u substitution. When I look at this problem, the function that seems to be inside of something else looks like this one. In fact, it's actually inside those parentheses. So I'm going to go ahead and say, let u equal tangent of x. And then I'm going to take the derivative of u. So the derivative of u is du. The derivative of tangent of x is secant squared of x, dx. And then I'm going to solve so that I have dx by itself, which would mean I need to divide both sides here by secant squared of x. So dx is equal to du divided by secant squared of x. Now I'm going to go back to my integral, and I'm going to substitute in whatever I can substitute in. So I had the integral of secant squared. The underlined part in red up there is going to become u, and and tangent was originally to the 3rd power, so that's going to stay. And then I'm going to replace dx with what I just found out that dx can be replaced with, du divided by secant squared x. Now I'm going to simplify anything that simplifies, so I notice that I have a secant squared x in a denominator and a secant squared x in the numerator, and I'm going to rewrite this, the integral of u to the 3rd du, which means now I can apply the power rule. Add 1 and divide by 4. Don't forget your plus c. And then my very last step is going to be to substitute back in the x portion that I was using u to hold the place of. So this is going to be tangent of x. I encourage you to pause the video and just start by just defining u, du, dx, and then unpause the video and see how you did. Don't work all the way through. Give yourself some time to just digest the first part here. So hopefully you've had some time to work. The inside function here is 4x squared plus 3. If I take the derivative of that, I'm going to get 8x dx. So if I solve for dx, I'm going to divide by 8x. I'm going to get that dx is equal to du divided by 8x. So that's going to get substituted in here. U is going to get substituted in here. Now, I encourage you to just rewrite the integral. Pause the video and rewrite the integral. So if I rewrite this integral, it's going to be the integral of x, I didn't do anything with this x yet, times u to the power of 3, and instead of dx, I'm going to have times du over 8x, oops, changed colors there, du over 8x. So now the x's are going to divide away, and I have an 8 in the denominator. And what I'm going to do is I'm just going to take that out in front of my integral for right now. It's just a scalar, and we learned when we learned properties of integrals that the scalar can be pulled out in front. So I have 1/8 times u to the third power du. Go ahead and finish this problem off on your own. Don't forget at the end to plug back in what you decided u was going to be at the beginning. So if I apply the power rule here, this is going to become u to the 4th over 4 plus c. And this now is going to be a denominator of 32. I have something to the 4th power plus c, and I'm going to plug u back in, which was 4x squared plus 3. So part of you should be sort of wondering, what happens if this value doesn't go away, right? It was really convenient here that secant squared and secant squared divided out, but what happens if that doesn't work out? And that's a really good question if that was coming to your mind. We're going to work on that in the next video. For right now, what we need to happen is going to happen, and we'll talk about later what happens if that doesn't work out so nicely. So all we're going to do for the rest of this video is work through some more practice problems and make sure we really have a solid understanding of the basics for u substitution. Okay, let's do a couple more together, and then I'm going to encourage you to pause the video and work through 5 and 6 on your own. If you're already feeling like you're kind of getting a handle on this, go ahead and pause the video now and see if you can work through 3 and 4 on your own. But we're going to get through a total of 9 examples in this video, so 7 more. I want you to make sure that you have an idea of what you're doing. So it's okay if you need to work through these first 2 with me. So I'm going to define u to be the inside function that I see, which is x squared minus 9. That means that du is the derivative of that, which is 2x dx. And if I solve for dx, I'm going to get that dx equals du divided by 2x. So that's going to get replaced here. Now I'm going to rewrite my integral. The integral of something cubed, and that something we chose now to be defined as u, times 2x, and dx we are replacing with du divided by 2x. Now I'm going to simplify anything that simplifies. Well, these 2 pieces are the same, and one of them is in the numerator and one is in the denominator. So I'm left with the integral of u to the 3rd du, and if I apply the power rule here, that's going to be u to the 4th over 4 plus c. And I'm going to substitute back in what u is. U is x squared minus 9. That is going to be to the 4th over 4 plus c. On number 4, it's not so obvious right away what the inside function is. It would probably be better if there were parentheses right here, because then I could tell that the inside function is 5x. We know how to integrate cosine, but cosine of 5x it is a chain rule. There's the cosine function, or it is a composition of functions. Cosine is the outside function and 5x is the inside function. So I'm going to define u. I'm going to say let u equal 5x, which means that du is 5 dx, which means if we solve for dx, whoa, undo that. If we solve for dx, we get that dx is going to be du divided by 5. And then I'm going to rewrite my integral. The integral of 5, the 5 that was already there, times cosine, but now instead of cosine of 5x, it's cosine of u. And instead of dx, it's du divided by 5. So this divided by 5 and multiplied by 5 are going to go away. So I have the integral of cosine of u du. What do I take the derivative of to get cosine? I take the derivative of sine. So this is going to be sine of u plus c. And then I'm going to plug u back in. And u on this problem was 5x. So I'm going to encourage you to try and work through 5 and 6, or maybe just one or the other on your own, and then unpause the video and see how you did. So here for each of these problems, I went ahead and defined u, and I took the derivative to get du, and I solved for dx. So pause the video and check over that part, and then see if you can rewrite the integral and work through the rest of it. Then unpause the video and see how you did. So here I have rewritten each of those integrals. Here, the x's will divide out, but I still have -7 and 8. So I'm going to just pull that in front of my integral. And then I'm going to apply the power rule and substitute back in what I know u is. So when I apply the power rule, I get u to the 4th over 4. If I multiply -7 over 8 by something over 4, I'm going to get -7 over 32, and I'm going to substitute back in the fact that u is 4x squared plus 3. Same setup on 6. These -4x's are going to divide out, so I just have u to the power of 1/3 du. If I add 1 to that exponent, I get u to the power of 4/3, and then I'm going to multiply by the reciprocal plus c, and then I'm going to plug in what I know u is, which in this case is 1 minus 2x squared to the power of 4 over 3 plus c, and that's going to be my final answer there. If you're feeling like you have a grasp on this, then I encourage you to try one more problem and see how you do. If you're feeling like you need more practice, don't worry, we're going to go through 3 more examples before we wrap up this video. Okay. I do, again, encourage you to pause the video, but I'm going to work through each of these problems start to finish in case you're feeling like you need a little bit more support. On 7, I'm going to define u to be the inside function. So I'm going to say let u equal 3x minus 1. So du is going to be 3 dx. And then I'm going to solve for dx. So dx is equal to du divided by 3. So now I'm going to replace dx with du divided by 3, and I'm going to replace 3x minus 1 with u. So I'm going to have the integral of u to the power of 10 times du over 3. So by defining u to be the thing that we're having trouble with in terms of x, it enables us to look at an integral that's now a lot easier to solve. We can just solve it using the power rule on this problem. This 3 in the denominator here, this is 1/3, right? I'm just gonna move that over in front of the integral. So that's gonna give me 1/3 times the integral of u to the power of 10 du. So 1/3 times, if I add 1 to 10, I get 11, and then I'm gonna divide by 11. So this is gonna become u to the 11th over 11 times 3 is 33, plus c, and then I'm gonna plug in what u was. U was 3x minus 1. Now, number 8 looks crazy because there's 2 inside functions. So what I want you to look at is which one has higher exponents. So there's definitely 2 inside functions. There's an inside function here. There's an inside function here. But if you look carefully, this is to the 3rd power, to the 2nd power, and this is smaller, to the 2nd power, to the 1st power. So let's see what happens if we let u equal t to the 3rd plus t squared. Then du is going to be 3t squared plus 2t dt. And then, dt, that's right. And then to solve for dt, I'm going to divide by 3t squared plus 2t. So dt, in this case, is equal to du, whoops, didn't mean to change colors there, divided by 3t squared plus 2t. Now, I'm going to rewrite my integral. There was a 3t squared plus 2t, and then there was the thing that I changed to be u. And then I'm going to multiply that by du over 3t squared plus 2t. And what you notice is that these 2 things are exactly the same. In a problem like this, if you accidentally defined u to be 3t squared plus 2t, what you would have ended up with was a problem where you still had t's and you have no other option. So that should indicate to you need to go back and define your u to be the opposite function. It's okay if that happens. You just need to go back and adjust. So this whole thing just simplified to be the integral of u du, which means this is going to be u squared over 2 plus c. And if I substitute in what u was, this is going to be t cubed plus t squared over 2. And if you look at this, plus c. If you look at this, if I took the derivative of it, this 2 would drop down and divide out. So I would have 1 times t squared, times t to the third plus t squared. That's right here. And then I would multiply that by the derivative of the inside, which would be 3t squared plus 2t, which is right here. So you can still check your answers. If you take the derivative of this answer, you should get the integrand here, the part inside the integral of what you started with. All right, last example. If you haven't tried one on your own, I really encourage you to do that here. We're going to let u equal theta squared. So du is 2 theta d theta. And if I solve for d theta, and it's okay that it's theta instead of x, the process is exactly the same. I'm going to get that d theta is equal to du divided by 2 theta. So I'm going to replace that here, and I'm going to replace this with u. So I'm going to have the integral of 3 theta times cosine of u times du over 2 theta. So my thetas will divide out. I still have a 3 and a 2. The 3 is in the numerator, the 2 is in the denominator, so I'm just going to pull that in front of the integral because properties of integrals allow me to do that. And then I'm going to ask myself, what do I take the derivative of to get cosine? I take the derivative of sine. The 3 over 2 is going to stay in front, plus c. And then lastly, I'm going to substitute in what I know u is, which is theta squared plus c. And again, I could take the derivative of that function to ensure that I get back to what I had there before. So key ideas in this section. Some integrals you can't evaluate using what we've been using before, just using the power rule. And the reason that that's happened in this particular type of problem is because we have a chain rule situation that we need to get rid of. The way that we undo the chain rule is by using u substitution, defining u to be the inside piece, taking the derivative of that and solving for dx, and then rewriting the integral using all of our new information. That should simplify to be something that's easy to integrate. Then after we integrate, or after we find the antiderivative, we're going to plug back in what we know u was originally, what we defined it to be, and make sure that we have our constant of integration. So go ahead and write down any questions you have, and I look forward to supporting you on this. Thanks for listening.